All right, hello, and thank you for joining me today. Give me just 1 second while I get this PowerPoint pulled up on screen. All right, and there we go. And again, thank you for joining me. My name is Mason Patty, and my project is an analytical comparison of a simulated PEM fuel cell and an internal combustion engine. All right, a little bit of an overview to begin. We'll start with what is a fuel cell, and then we'll work into background on my project. And we'll start with application one, go over assumptions, some calculations, then we'll work into the simulation and analysis. And as far as application two, not too much has been done on application two. As you can see, all of those symbols down there are highlighted in red, as we hadn't really gotten too much to it. So, all right, let's get into it. So to begin, what is a fuel cell? A fuel cell is an electrochemical device that converts chemical energy into an electrical energy. It takes chemical energy from a chemical reaction and then takes those electrons, pushes them through to produce an electric current. Hydrogen is the most common fuel source for fuel cells, but there's a multitude of different kinds of fuel cells, and they do take a wide range of fuels, but hydrogen is the most common. The overall chemical reaction inside of a PEM fuel cell is represented by the chemical reaction below on screen. And the figure on the right just kind of shows a general schematic of how a fuel cell works. Hydrogen enters from the left, it hits the anode, and the anode takes an electron away from the hydrogen, pushes that electron through a wire, produces a current. The hydrogen moves to the electrolyte, combines with the oxygen, and produces water as the product. Okay, and a little bit on the background of my application. So the first application is a comparison between fuel cells and combustion engines in automotive transportation. The second application is a comparison between regenerative fuel cells and batteries for lunar power. A multitude of fuel cell types, meaning fuel cells can be used for a wide range of purposes, and parameters such as lifetime duration, lifetime cost, efficiency, and power density will be calculated and compared to literary references. All right, so assumptions for application one. So the fuel cell will be a proton exchange membrane fuel cell, as it is widely accepted as the best fuel cell for automotive transportation due to its small size, lightweight, and quick startup time. Because of the quick startup time, this will be a low temperature fuel cell. So, and the fuel cell receives hydrogen at standard conditions. In production, the fuel cell is a part of a production line of 500,000 units. The PEM fuel cell will operate without combined heat and power due to low operating temperature, as mentioned before. Water exits the fuel cell as a saturated liquid. The thickness of the electrolyte is 15 microns because this is the recommended thickness for automotive applications. The transfer coefficient is 0.5, and the fuel cell operates at 70 degrees C, as low temperature PEM fuel cells operate between 60 and 80. 70 is kind of that balance point. All right, so the lifetime calculation. So how you do a lifetime calculation for a fuel cell is you first have to do some experimental testing on it. And you do this experimental testing to determine its degradation rate. And this figure on screen shows real performance. That is experimentally determine the degradation, and you extrapolate that into the future to determine, okay, it's going to fail. It's going to reach this failure threshold at this time. And that is how you determine the lifetime of a fuel cell. You can do this through experimentation or simulation. For me, I'll be doing it through simulation. So taking that figure from the previous slide and putting it into an equation form gives you the equation you now see on screen. And the degradation, the overall degradation, so how much voltage I can lose in the lifetime, is the numerator. And then the denominator are the factors that contribute to our degradation. And you can see what each individual variable is listed on screen. So how we calculate efficiency is based on, excuse me. So the efficiency is found by taking the quotient of the output electrical power and the power potential of hydrogen fuel. So how much power can this hydrogen fuel give me, and how much power do I actually get out of it? That gives us our efficiency. How we determine the power potential of hydrogen, we determine that using Faraday's law, and that is the second equation that is seen on screen. The power potential of hydrogen can then be found by taking the product of the molar flow rate and the higher heating value of hydrogen. And we use the higher heating value because the water leaves as a saturated liquid. Okay, now for the power density. So the power density is the product of the output voltage and the current density. The output current density is found from a polarization curve, and where K is the slope of the linear section of the graph. So the top figure on the right shows a polarization curve for the anode. And since alpha was equal to 0.5, the anode and the cathode curve look exactly the same. And the figure on the bottom is that anode curve kind of zoomed into the linear section, and it shows a line going with that linear section. And that the slope of that line is our area square resistance, or ASR. Okay. And then this is the actual block diagram for the fuel cell. So the fuel is made in the very first function there, and then that is how we get our maximum voltage. And then that maximum voltage we use to determine our power, and the power determines our current density. Current density determines our losses. We have to have that feedback loop in order to get back to the losses. Okay. And then for energy analysis, the amount of hydrogen and oxygen needed is found from chemical properties. Water production is found in a similar way, and heat production is found from the amount of losses. The amount of energy that we didn't get to use is the amount of energy that was put into heat. So, and then here's some of our results from that. This is the same Simulink model, but zoomed out a little bit. That fuel cell model is inside the block on the far left of the screen. And then inside each of those middle blocks is just a little block diagram for doing some math to determine the output. And you can see on screen the oxygen flow rate, the hydrogen flow rate, the water production, the heat production, and the efficiency. The one thing to note is that all of our flow rates are kilograms per hour per centimeter squared. So this is based on the active catalyst area, as I did not use a surface area anywhere in my calculations. So everything is in terms of area. Okay, and then for a literary comparison on application 1, the lifetime cost of a compact internal combustion engine vehicle is about $48,000 over a 20-year lifetime. Over the lifetime of the internal combustion engine, it will produce about 137 pounds of greenhouse gases. Gasoline combustion engines operate at an average of 20% thermal efficiency, but diesel combustion engines can increase the efficiency to 50%. And then some issues to overcome for application 1. So first, some general issues with PEM fuel cells. One, the cathode and anode both use platinum as a catalyst, and platinum, aside from being very expensive, it also deteriorates quite quickly as a catalyst. So that has to be replaced often, and that just increases the price greatly of a fuel cell. The hydrogen fuel is highly sensitive to impurities. So the hydrogen fuel, it won't actually, if it's impure, it won't actually ruin the fuel cell. From what I've read, it will more just kind of damage stuff like the gaskets and the internal components, and make the lifetime less on it. But it's not going to cause it to do anything hugely detrimental. Future recycling companies may also have issues distinguishing the type of fuel cell and cause damage to the parts. So the way you disassemble a PEM fuel cell and a solid oxide fuel cell are completely different. And somebody who may not be able to tell the difference between them may take them apart thinking one thing, but meaning the other, and destroy perfectly good parts. So those are some general issues with PEM fuel cells. Specific to my project, I'm having issues with Tafel plot generation to determine the reference exchange current density. I believe that's one of the sources of error, and that's why my output power is a little bit too high. Has to do with that. And moving on, that brings me to the power density verification. The power density, like I said, it's a little bit high compared to other results I've seen. And I believe the Tafel plot in determining the exchange current density that way will give me better results, but we've got to get around to that. So, okay, and then a little bit on application 2. Draft outline. Regenerative fuel cells work as an energy storage system that would be an alternative to batteries. In a lunar application, regenerative fuel cells would be used to store energy in a more efficient measures than batteries. Regenerative fuel cells operate as a reverse fuel cell. Instead of exchanging hydrogen fuel for electrical energy is exchanged for hydrogen fuel. The hydrogen fuel is immediately available for use when electrical energy is required. So this is a way of producing hydrogen fuel aside from reforming or other ways. And then like before, parameters such as lifetime, energy stored per volume, energy stored per mass, and emissions will be calculated and compared to literary results. A little bit of the motivation behind this. So the lightweight of regenerative fuel cells offers an opportunity for mass renewable energy storage with solar arrays collecting energy while in sunlight and discharging the energy into RFCs while not in the light. So batteries are inefficient for this application because of their weight and relatively low lifetime compared to an RFC. And the use of an RFC would also be a greener choice because batteries require hazardous chemicals, and these hazardous chemicals need careful disposal. And then a little bit on the objective. So RFCs and batteries can each store energy based on their mass and volume. So their respective specific powers and energy density will be computed and compared. Cost analysis will also be conducted to determine the cost of production for each storage system and lifetime costs. Emission levels will be measured based on how much chemical volume must be disposed of per amount of energy stored. Okay. And then here are a list of my references, and thank you for your time. Hope you have a wonderful day.